When we want to think about how enzymes work and we consider the piece of substrate specificity, the lock and key model is a pretty simplistic and, as I hope to show to you, very idealistic way of kind of thinking about this. So highlighting, we're going to talk about this idealistic view. And then when we finish, I'm going to sum up with what is a more energetically, thermodynamically realistic picture of how enzymes bind their substrates. So this lock and key model, again, is really great for thinking about substrate specificity. Right? We use this when we talk about, this lock and key model, even when we talk about how we think about how insulin works, right? Insulin is kind of the key that opens the lock, if you will, to let glucose into your cells. So it's a very simplistic way of thinking things, but it sort of makes sense, right? We think about substrates being like a key. And as we just think about keys in our everyday life, they fit into certain locks. And we can use sort of energetics and a hierarchy of intermolecular forces to help explain a lot of what we see here. So just kind of zooming in down here, here's this hierarchy of intermolecular forces that we've talked about, right? This is nonpolar interaction. So we've got London dispersion forces. So we've got surfaces that are touching and interacting with one another. That helps explain why a lock only binds a certain key. We might have high on our kind of hierarchy list, our electrostatic or our charge-charge interactions. So those are our electrostatic interactions. Here we can see we've got hydrogen bonding. I just don't have specifically dipole interactions that's shown here, but here is the hierarchy of intermolecular forces that sort of explain why certain keys are going to fit into certain locks, why certain substrates are going to bind only to certain enzymes, or why certain enzymes only bind certain substrates. So the key piece sort of to this lock.
Okay, I found this on the web.
The key piece for this lock is understanding how we've got a certain molecular shape, okay? And that's going to then fit into a complementary enzyme active site. Okay, so we're going to revisit this picture here, but I want to take a second and just kind of highlight how we are going to think about enzyme binding substrate, doing chemistry, and so forth. And this is going to lead into our learning unit on kinetics in terms of understanding how this works. So we're going to abbreviate enzyme E, and then substrate is S. So one of the things that we'll talk about is the fact that enzyme binding substrate is a reversible process. So enzyme binding substrate is reversible, and it's going to generate an enzyme substrate complex. Okay, we'll deal a lot more with that complex. We call this the Michaelis complex. We'll deal with that in our learning unit on kinetics. But then we're going to have chemistry happen. I'm going to move this down here. So we're going to have chemistry happen. And when that chemistry happens, then we generate an enzyme product complex. And importantly, another spot that we need to think about is that we are going to have the release of that product to then have enzyme and free product. And why this is important is if we want to have this enzyme kind of come and do additional chemistries, this is what we call turnover, it has to release the product that's sitting in its enzyme active state. So if we want to repeat this process, or in enzymatic speak, we call this enzyme turnover, we have to have that enzyme release that bound product from its enzyme active site so it's free and available to bind another substrate. So we're going to see this sort of equation, if you will, in our next learning unit on kinetics. But again, this is going to help us think about this piece right now, this binding piece, this enzyme binding to substrate, this lock binding its key. So what I hope to highlight for you here is that when we truly think about the energetics of this, we'll understand that this lock and key model is overly simplistic and idealistic and actually not realistic when we consider the energetics and the thermodynamics of this process. So what I want us to think about is entropy and enthalpy. I want us to think about these as they occur for specifically the enzyme, and we're going to consider what happens before we bind substrate and then what happens after we bind substrate. So let's think about entropy. And remember, when we think about entropy, you want to think about that phrase, more molecules moving more. So anytime we do something to restrict molecular motion that is unfavorable from an entropic standpoint, right? We talked about that with protein structure, secondary structure formation. When we form alpha helices or when we form beta strands that interact to form beta sheets, forming those coils or those zigzags is energetically unfavorable from an entropy standpoint. Well, what did we do with it? We had an enthalpic compensation. We had hydrogen bonding that occurred to sort of offset that entropic penalty. So keep that story in mind as we talk here about what happens when we have an enzyme that we're asking to kind of adopt a specific lock shape. So again, when we think about entropy of the enzyme, and this is going to be before we bind our substrate, okay, and so we're saying is it's in this lock shape, okay. What we call this in terms of structure formation is we say that it is pre-organized, okay. So importantly, we see that this is going to be highly unfavorable entropy to pre-organize. And so that's the term that we're going to use, pre-organize our active site into that lock shape. Okay, so it's unfavorable to form that lock shape and freeze out that molecular motion if we don't have the key bound there. Now, importantly, we can see all of these intermolecular forces that happen there, but they don't happen until the substrate binds, until the key goes into the lock. So when we think about this enthalpy compensation, so when we think about enthalpy here, and I want us to think about that enthalpy after we've bound our substrate. Okay, now after we've bound that substrate, okay, so after we've formed our complex, okay, now we are going to get that compensation. Okay, that is going to allow us to compensate for that unfavorable enthalpy. Okay, so thinking about what's happening here, enthalpy after binding substrate is going to be favorable. And that is because we have formed all of these intermolecular forces. So formed these new intermolecular forces, right? We get London dispersion forces, we've got electrostatic interactions, maybe we've got some dipole-dipole interactions, we've got some hydrogen bonding, but importantly, these new intermolecular forces are going to be that compensation. Oops, and I wrote enthalpy here. Sorry about that. This is going to be compensation for our unfavorable entropy. Sorry about that. So these enthalpic contributions from these new intermolecular forces are going to compensate for our unfavorable entropy that happens if we consider pre-organizing the enzyme active site, if we consider a rigid lock that is going to bind a specific key. All right, so I'm going to flip to another slide here and highlight that, you know what if most of this is true, but we don't want to pre-organize our lock too much. So this is what we call the induced fit model. And in the induced fit model, what we're going to be able to do is think about how we might have a mushy lock, if you will. So I want to highlight here, if we look starting sort of right here at this enzyme substrate complex, this is kind of where the lock and key model kind of takes off. So we're going to have the lock and key model is going to be here, but this induced fit is going to be a more realistic view from an energetic standpoint. And it's going to look just a little bit further back, and it'll say when we don't have that substrate bound to the enzyme, when we don't have the lock in the key, what does the lock look like? And what we're really going to see here is that our lock is going to be a little bit mushy. Our enzyme active site is mushy. So our enzyme active site is mushy. I know we tend to use, weird adjectives here, mushy, fluffy, things like that to describe things, but it's really kind of a neat way of thinking about what's going on. It does sort of look mushy. It's not fully pre-organized, but importantly, why that's helpful is it's going to be favorable from an entropy standpoint, or really we could probably say it's less unfavorable entropy. We allow that lock to have a little bit more fluidity, a little bit more molecular motion, so it's not as much of an entropic penalty. We're still going to get that enthalpic gain when we bind our substrate, but we're not having to pay a cost too much upfront without having the substrate be bound. Okay, so induced fit model has a lot of the hallmarks that we see of a lock and key model, particularly once we consider the enzyme binding to the substrate. But the key difference is it's a more realistic energy view, an entropic view of what the enzyme active site likely looks like before binding substrate. Is it probably is not as rigid as the lock and key model might suggest.